In this video, we're going to answer the following physics energy problem. Here we have a roller coaster loop where a car starts at a height h, falls down the loop, and enters into this circular loop here with radius r. So the question is, show that the difference in apparent weight at the top and bottom of the loop is 6 times the weight of the car, 6 mg, which is the same thing as saying 6 g's. So first, it's important to define what apparent weight is. Apparent weight is equal to the normal force experienced at a point. Okay, so with that in mind, what we're trying to find is the difference between the normal force at the bottom minus the normal force at the top. And I'm doing it in this order because we're expecting the apparent weight to be more at the bottom. You know, you have that experience when you're in a roller coaster. When you're at the top of the loop, you have a feeling of weightlessness. So we know that weight should be less. So we're going to put it. So we're going to subtract that from the bottom. We should get 6 mg. Now let's go through the steps to figure this out. So what we're going to do now is look at the loop when it's at the bottom. So here's the car, and this is a free body diagram here, so what we're going to do is label the forces. We have a downward force, mg, and we have an upward force, Fn, the normal force. This right here is the apparent weight, and we want to find an expression for it. This is going to be for the bottom. So we know that the centripetal force in a circular path is always pointed towards the center of the circle. So we have the centripetal force is the normal force that's pointed towards the middle of the circle, Fn of the bottom, minus mg. Now that mg force is pointing away from the center of the circle, that's why we're subtracting it here. Now we can also find an expression for the centripetal force at the bottom. Now the equation for the centripetal force, mv squared over r. So we have mv bottom squared divided by r. Now that's equal to the normal force at the bottom minus mg. So what I'm going to do here is just rearrange to solve for the Fn at the bottom. Fn bottom equals mv bottom squared over r plus mg. Okay, so we solved for the normal force at the bottom of the loop. Now let's solve it for the top of the loop. Here's our car again. So at the top we have gravity always pointing downwards. We also have our normal force. Now if there's a normal force, it means that the speed of the car is great enough to stay on the track. If that normal force becomes 0, that means that it actually won't complete the loop and it'll actually just fall off the track. So let's write out our centripetal force at the top. We know the centripetal force at the top will be mv top squared over r. And that's going to be equal to mg plus Fn at the top. So again, let's solve for the Fn at the top. Fn top equals mv top squared over r, this time minus mg. So what are we trying to find here? We're trying to find the difference between Fn bottom and Fn top right here. Normal force at the bottom minus the normal force at the top. So what I'm going to do now is subtract these two quantities. So right here. Fn bottom minus Fn top equals mv bottom squared over r plus mg minus this here, minus m v top squared over r. Now we're subtracting a negative, so we're going to add mg. Now this is going to simplify the two mg's add together, they're like terms. So what we're actually going to have here is m over r times v bottom squared minus v top squared plus 2mg. So all I did here was distribute out an m over r. You see we have an m over r here, an m over r there. I just distributed it out and make it an expression that we could work with. So in order to find this difference, we need to find out what the difference is between the velocity at the bottom squared and the velocity at the top squared. This is where energy comes into play. You see here we haven't done anything with energy, and we know it's an energy problem, well, mainly because I told you. So what we're going to do now is we're going to use a conservation of energy equation to find out this expression here. So here we're going to do conservation of mechanical energy. Alright, so we'll call this point here our initial point. We'll call this point at the top our final. So our kinetic energy initial is equal to 1/2 mv bottom squared. Simple enough, right? Just the velocity at the bottom, and we don't really need to find that out. We're not even going to use h in this case. So our potential energy at the bottom is going to be 0, because we're just going to call this our this is going to be a reference frame where the potential energy is 0. So I'm not even going to write that down right now. The kinetic energy final is equal to 1/2 m, and can you guess what comes next? V top squared. And this time we do have potential energy at the top. Now, if the radius of the circle is r, that means that the height at the top of the loop is 2r. So mgh is our equation for potential energy. This time it's going to be mg times 2r, 2mgr. Alright, so we're really almost done here. What we do is we set an equation for conservation of mechanical energy. What we say is that the kinetic energy initial is equal to kinetic energy final plus potential energy final. 1/2 m v bottom squared equals 1/2 m v top squared plus 2 mgr. See how the m's will cancel here? There's one m in each term. And what we can do is we can actually divide by 1/2 through. So what I'm going to do is divide by 1/2, canceling this. And if we divide 2 by 1/2, this is actually going to change to a 4. So we have v bottom squared equals v top squared plus 4gr. So remember, we're looking for this expression here, v bottom squared minus v top squared. So what I'm going to get is v bottom squared minus v top squared equals 4gr. That's what we're looking for. What I'm going to do is I'm going to plug into this expression here. And we're going to finish up in this little box. So we have the difference between the normal force at the bottom and the normal force at the top is equal to m over r times 4gr plus 2mg. Look what happens here. R's cancel. 4mg plus 2mg is 6mg. Our final answer matches up with what we're given. And look, it doesn't depend on either the velocity or the radius of that loop. The only thing that matters is that there's enough speed to get around, or else obviously we couldn't calculate the difference in apparent weights.